Ladies and gentlemen, recording has started. So, on Wednesday, we started in on the next section dealing with, one thing, if you are watching, the fans are on, so sometimes you might hear like a little breeze, so it is still kind of hot here, but complaining about it won't make it any cooler.
Yesterday, we were walking around the school in the study hall, and there was like, right when we walked into the side thing, there's like,
yeah, isn't it weird?
Yeah, it was,
you know what's actually really weird is if you start over in English and you like walk down the
hall,
you can feel it like getting hotter as you walk down.
And then right there, like right here, just like you just think
it's so cold.
What?
Like the office. I don't know what hall it is.
Oh, like down by the office. Yeah. Yes, sir.
The English room was pretty hot. The nice room was pretty hot the other day, right? Down there. And that too, without the AC was kind of broken.
Unlucky.
Math was the worst.
Yeah, math.
So actually, English is like with English. If the air conditioning is broken, it's pretty bad because there's like no windows over there.
There wasn't even a fan.
Well, because like there's no windows, so it's like I don't know. I mean.
Math.
Can we put
Yeah, that's right.
It's pretty much science in the next to the class.
We do have some
Fourth language is English and math. I'm just like, but my computer has cuts.
I like Spider-Man.
All right. What?
Really? That cold?
Yeah, it's nice.
Wow.
All right. On Wednesday, we started in. On Wednesday, we started in on this idea of nuclear energy. And we talked about the idea that the nucleus of an atom is a huge source of potential energy. And why is the nucleus of an atom such a huge source of potential energy? Well, it's so small, yeah, but that's not really what makes it a source of potential energy. Chris?
You have all those protons in there that are repelling each other.
Right. We have all those protons that are sitting in there, and they're all trying to repel each other. And after a while, if you get too many protons there, right, you get above 82, and then all of a sudden, well, not all of a sudden, but that repulsion force from all those protons trying to push each other away becomes stronger than the force that's holding them together, the strong nuclear force, and they start sort of breaking apart. We talked about the idea that when it breaks apart, we can use it to do stuff then. Okay? If you go ahead.
You know, it's like if one atom, like something just like how noticeable would it be?
Hold on to that question because we'll get to that just a little bit as far as the actual numbers. We're going to get there. The answer is not very much. Okay, that if one atom being radioactive, easy. One atom being radioactive really isn't an issue. It's when there's a lot of atoms being radioactive that's when we get that issue. Okay. First question, are you good? All right, we're good here? So then, we talked about the idea, or at least introduced the idea of nuclear fission. Is that correct? So, first, I believe I spared you guys, or I can give you guys some of the details as far as where we're going. But I think we talked about it in context a little bit, right? Okay. So first, fission comes about by some experiments. Fission comes about by some experiments done by this lady, Lisa Meitner, and this guy, Otto Hahn, who were both working in Germany on this sort of thing. What?
In spite of Tom being super smart.
Hey.
Settle in.
You move out in the hall? Or?
He keeps taking pictures of me.
Dude, that's so weird.
So, we're in Germany, okay? It's the 1930s.
Germany or Austria?
Meitner is from Austria.
Ooh.
She's also a Jew, but she's working in Germany.
I totally
So-
did I not tell you on Wednesday that I think it's Austria?
So, well, she's from Austria, but she
I know.
was,
I mean, like, her name is
Right.
definitely
Okay.
Austria.
But anyway, so she's an Austrian Jew working in Germany in the late 30s. Okay? So what does she decide to do? She decides to leave Germany because that's a good plan for somebody who's Jewish at that point in time. Okay? So anyway, she moves actually to Sweden. And
That's interesting.
this is usual. Okay. So she moves to Sweden, but this guy, Otto Hahn, who she had been working with for a really long time, continues to work on these experiments that they were working on, they were setting up, and he sort of like does the experiment and sends her the results, and then she sort of interprets them and looks at them, and she kind of sends it back to him, and they
Where
sort
did
of.
he live again?
He's in Germany. He's still in Germany.
Has he found your features?
I don't believe so.
He's German.
I think so, yes. Although I didn't really research him all that much.
Do they like each other?
I think they're just like colleagues. So, yeah. Anyway, so they're corresponding. Then they do. Hahn does this experiment like in 1938, and then Meitner gets together with Otto Frisch, who is her nephew, and they sort of interpret this experiment in 1939 and put out this paper about fission. And said, yeah, I think we can do this. Okay? And they sort of show mathematically that it all works out and everything's good. Okay? Did we talk about like larger context of where we went after this? Okay? So, time frame, right? 1939. I think all of you got gathered from what we've discussed history-wise, where you are in history class right now. Okay, 1939, right? World War II is starting. Okay, tensions are high. Say again. Yes. Okay. But in this case, in 1939, actually, though, that's when the Nazis invaded Poland, I believe, right? So in Europe, this is already going on, you know. So there's scientists there, a lot of scientists in Europe, who either are Jewish or just being, you know, educated, rational people, kind of see what is going on and they bail. They're like, I gotta get out of here. Okay? And a lot of them come to America.
Like Albert Einstein.
Like, well, actually, Einstein was here already, but he was here already. But yeah, I think if I remember right, he may have kind of seen it a little earlier and just sort of bailed. But anyway, Einstein is an important part to this story, Raj. Okay, so in the early 40s, okay, all these scientists and they're doing work on this fission, and they start seeing where it's ultimately going to lead, and they see the atomic bomb, right? And they know that they're not the only, the scientists in America know that they're not the only ones who have this information. German scientists have this information as well. So, what sort of sets the whole thing in motion, actually, Neuron, is Einstein. Because at the time, like early 40s, late 30s, he's Einstein. Like, he's not just some, like, he's done all of his really kind of important work. He's famous, and, you know, he's like Einstein as we think of Einstein. Okay? But that also means that he has a lot of clout, that people trust him and understand what he's saying. And he's not really working on this stuff, but he obviously understands it. And so all these scientists who are working on this stuff sort of come to him and say, all right, this is what we think is ultimately going to happen, and that being the atomic bomb. And we really think that we better build this bomb first, because if we don't, the Germans are. So Einstein goes, okay. So Einstein writes a letter. He writes a letter to FDR. And says, thank you. He writes a letter to FDR and says, hey, we better do this, because if we don't, they're going to. And FDR says, well, he's Einstein, so I better listen to him. And so that kind of gets, I mean, he's a freaking Einstein.
Wait, Albert Einstein didn't come on with like for the actual picture.
Dude, wasn't he Russian actually?
Oh yeah, what?
Einstein is Austrian as well. His parents.
Oh.
Austria is cool. Like,
Yeah.
they have a lot of.
Austria doesn't get a lot of credit, but.
I know they're.
I mean, actually,
Mozart's from
I
Austria?
can't remember who. I don't think it was your class, but
Mozart.
also we were talking about Meitner because she's Austrian, and actually we talked. I can't remember if I remember
Isn't
in
like
class.
Bach and Mozart?
Yes, I don't know exactly who.
Pretty sure Mozart.
But anyway, element number 109 is named Meitnerium.
You told us that.
And so we were, like I said, I don't think it was this class, but we were talking about, like, you know, that she's a famous Austrian. And I was like, I can't really think of any other famous Austrians. I forgot about Einstein. But someone else
And
said,
Mozart.
another famous Austrian? Anybody?
Mozart.
Well, Mozart, yeah.
It was Austria.
Hitler's a famous Austrian. he probably didn't make it into the Austrian Hall of Fame though. So they probably.
How about the people How about the
There you
people
go.
from the sound of
Is
music?
that really,
Yeah.
is that really
Good
good?
fictional Austrians.
Yeah.
You know, so.
Finding whatever.
Anyway,
They never make
the Von Traps.
You know what?
But anyway, so Einstein writes his letter to FDR. That sets the whole Manhattan Project in motion, and ultimately ends up with us dropping atomic bombs. Okay. Just another kind of sort of side note. Einstein feels really bad about writing the letter when he sees, what ultimately ends up happening. And actually, too, Oppenheimer, the guy who's in charge of the Manhattan Project.
Sounds like
What's the Manhattan Project?
It's where
Oh, there's a movie, really good movie.
Somebody's
on Manhattan
some
Project.
history teacher's gonna be mad if you don't know that. So.
It's a really good movie. You should watch it.
I've never seen it.
It's a really, really good
The Manhattan Project. The Manhattan Project is our
Scientists can.
quest to build the atomic bomb.
It's awesome.
So anyway,
I've heard of it, we just never
Then they
talked
die,
But-
it's going on with the uranium, and then it drops in after using it. It's exposed.
They're being very disruptive.
so that's probably not helping either. Although, in the grand scheme of things, you dropping a pencil is a lot less disruptive than other things that are going on. So anyway, hit me. Go ahead.
It's like
No, there's.
Bear with
Yeah, they went out in the desert, and were far away from everybody. Basically secluded everybody that was working on it and said, "You're not leaving here until you make the atomic bomb," and that was kind of about it. So
What was the name of the guy who first like came up with the idea?
it wasn't
I
just
mean, not
one.
the idea, like.
It's a bunch of different pieces that come together. Anyway, so anyway, that's where fission comes from and all that. Okay, and I think before we left on Wednesday, we had looked at this picture, right? Okay. All right, let's review. So, we start off with a radioactive nucleus, okay? And I think we talked also about the idea that not any old radioactive nucleus will do this. Is that correct? We discussed the idea.
Yeah,
You can't just pick any radioactive atom and do this with it.
this would be uranium 235.
Well, uranium-235, there's also a plutonium isotope that does it too.
Or
and-
uranium 238.
No, not uranium-238. That's the problem. Okay? That most of the uranium that is out there in the real world is uranium-238. But uranium-238 won't do this. When we shoot a neutron at uranium-238, it doesn't kind of split in half like this. It just sort of like, the neutron sort of like globs together and then like a little chunk falls off. Instead of like splitting it in half. And the really important part is not so much that the chunk is falling off or that this big atom is splitting in half. These two things are the really important parts. These extra neutrons that come out. And that's what we're going to talk about. That's where we'll end up today. Chris, go ahead.
Now what makes it like split in half?
Okay. It has to do with the idea, okay, yes, the number of protons contribute to the instability of the nucleus. But it also has something to do with the balance between the number of protons and the number of neutrons. Certain ratios work better than others. They just do. These are what we see. Okay? So shooting this extra neutron in there makes it just really unstable. And the way that this decays in that case, it really becomes uranium-236 for a second. And then the way that decays, it decays like this, and it falls apart this way. I don't know if there's a reason. I'm sure you can probably find out a reason why, some big explanation, but I don't really know what that is. But the important thing being, though, that this doesn't happen to all nuclei. It only happens to certain nuclei. And right now, we've found two that do it. Uranium-235, and then it's a plutonium isotope, but I can't remember the mass number of it. Okay, go ahead.
And those neutrons that get shut out, they go to the uranium.
Right, that's where we're going next. Okay. So go ahead.
Do the small neutrons have the same amount of energy as the bigger ones, but just because of their size, they just seem like they go up? Like, do you
They're
understand?
probably moving faster than the big ones just because of the whole mass acceleration relationship. Although, when you say do they have as much energy,
Or like radioactivity.
it's kind of hard to say because of the idea that these are bigger, so could these do more damage than that one? Yeah, it's a little hard to say, you know. Allison, go ahead.
Are those, like not the really small neutrons, but
Yep.
like the nucleus, are they not radioactive?
Those aren't radioactive because if we look at them, krypton, its atomic number is 36, if I remember correctly. Yeah, I think so. And then barium's atomic number is 58, no, 56. Okay, so we're in that range now where there's not as much outward push from those protons because there's not as many of them there. So technically, these two aren't really radioactive, or at least not radioactive in the way that uranium is. Okay. So we got this going on, right? So we talked about that we shoot a neutron at this nucleus. Okay. And did we talk about why we use a neutron and not the other stuff? Okay.
It's big enough.
It's big enough to cause the nucleus to split. But if it was a proton, would the proton ever get there? No, because of the whole repulsion idea. Right. And that means that we end up with these two smaller nuclei. But really important, on the other hand, is the idea that we end up with lots of energy and then 2 or 3 extra neutrons. Okay? Now, why the energy? Here's why the energy. If you take a look and you can make very, very precise mass measurements, what we find out is that if you took the mass of this uranium-235 atom and this neutron together, okay, added those together, because these are like the reactants of the nuclear reaction, right? This is what was there before. And then you take the mass of this krypton nucleus, this barium nucleus, and then these 2 neutrons, and added them together, what you find out is that there's actually a small amount more mass in the reactants than the products. That the mass value actually goes down, which may seem, obviously contradicts something that we talked about earlier, right? What does that violate? Conservation of mass, right? That there is a change in mass. So where does it go? That leads us to the next part, the idea of mass energy equivalence. Okay? So, 1905, Einstein publishes a paper not relating to fission or fusion in any way, shape, or form, because, right, did we even know about fission and fusion in 1905?
No.
What was discovered in 1905?
Radiation. No radioactivity.
Anybody?
Oh, man.
The nucleus. Okay? Anybody remember the scientist that did the experiment that discovered the nucleus?
Goldberg.
Rutherford.
Rutherford.
Okay? Goldberg. No. Rutherford. He did the gold foil experiment, though. How's
Yes,
that?
that's what I was thinking.
That's what you're thinking, I'm sure. All right. But Einstein throws out this equation. Like I said, in a different paper, nothing related to atoms in any way. Because they don't even know about a nucleus, let alone being able to even think about dreaming of splitting it apart. Okay? But Einstein throws out this equation, E equals mc squared. Probably the most famous equation out there. Is it the most practical equation? Maybe not, but definitely the most famous.
Why is
Okay?
it so famous?
It's just because it's like, I mean, it actually is really quite powerful.
What is C?
So, let's go through, right? What's E going to stand for? E is going to stand for energy. Einstein. Actually, if it was then, it would be much greater than sign, because Einstein is obviously better than everybody else. E greater than infinity. So, anyway, so E stands for energy. M is going to stand for what? M is going to stand for mass. Then the missing piece to this equation is the C part. C represents the speed of light. Okay? The speed of light is a really, really large number.
Yes.
Light travels at 3.0 times 10 to the 8th meters per second in a vacuum. Okay? It travels a little slower when it goes through air or water, but not a whole lot. That's 10 to the 8th, yeah. That means it's 300.
But I was expecting to be like 10 to like at least. What is that? No,
It's 300 million meters every second.
Oh.
Is that not fast enough?
Oh,
That's good.
You're saying close back really fast.
Anything, go ahead.
How did he calculate the speed of light?
The speed of light is a known value. That's something we measure. Okay? That's not what this equation was used for. What Einstein is saying here, okay, is that if you look at this equation, okay, the left side of this equation has energy on it. The right side of this equation has mass on it. If they're on opposite sides of the equation, what does that mean? They're equal. That energy and mass are the same stuff, just in a different form. And that if we can somehow convert mass into energy, mass is on the right-hand side of this equation. It's also over there with c squared. C is times 10 to the 8th. If you square it, it's 10 to the 16th. So you're talking about something that's 10 to the 16th power over here on the right-hand side of this equation. Even if you plug a really small amount of mass in here, how much energy does that equal? A lot. Okay? So Einstein doesn't figure out the speed of light. That's something we measure. But he uses it to show the equivalence between energy and mass. Now, something that we have to keep in mind. Okay? What this equation is not telling you is that if you take mass and make it go really, really, really fast, like the speed of light, it's not going to turn into energy. That's not what that equation says. The c is just sort of a proportional constant that gives you the right number. Okay? But, like we said, what that's saying is that if you have mass, you can get it into energy. That they're really the same thing. So somebody in the first class asked a question about two laws that we've heard so far this year. Right? We've already talked about that looking at the mass values, we're sort of violating conservation of mass. But if we're just creating energy out of nowhere, what else does that violate? Conservation of energy. However, if you put the two of them together, does anything get violated? No, because they're all sort of interconnected. Okay. Let her go. People worry about the okay. All right. So what Einstein says, although he doesn't actually say it in this case, what Einstein's equation is used for is, if it ever shows up here, that if we can take a small amount of mass and turn it into energy, we get a whole lot of energy. And that's what's happening in a fission reaction. That some of the mass of the reactants is being converted into energy. Now, also something to consider. We talked about in that E equals mc squared, the right-hand side, the mc squared side. You're talking about something that's like 10 to the 16th power. Okay? The mass of one atom is like 10 to the minus 27 kilograms. So are you getting a lot of energy out of one atom going through fission? If you have a 10 to the minus 27 times 10 to the minus or 10 to the positive 16th, you're still 10 to the minus 11th power, right? Does that make sense? Going through, okay. So if you have one atom that goes through fission, do you get a lot of energy? No. But if you get a significant amount of atoms, which we talked about, like 1 gram of something is a huge amount of atoms, now you get to the point where you can start getting some tremendous amounts of energy from, in the big picture, not very much mass. Kelly, go ahead.
Like, instead of just saying it as heavy, like, what is that energy amount, like, related to? Like, what would, like, 1 gram, like, how much energy?
We could plug it into that equation and figure out. It's in joules.
Okay, yeah, like, that's right. Like, what is a joule? Like, what would that be like?
Okay. So, a joule. Caroline, this is 1 kilogram if I stick these two things together. Okay, they're each 500 grams. If I make this 1 kilogram mass go 1 meter per second, 1001. Okay? How much this would hurt running into you going that fast? Okay, 1001.
Yeah.
1 kilogram, 1 meter per second, that's 1 joule. Okay? So how much that would hurt running into you is 1 joule. If I turn 1 gram of mass into energy, that's 10 to the 13th joules. Does that make sense?
Yeah.
Okay. So yeah, does that help as far as a
Yeah, I
perspective?
just like didn't really.
Yeah. Good.
But that's good, like, when they find something that can go faster than them.
That has been other than Usain Bolt, obviously. So
How fast is
that has been sort of discredited. Recently, it came out that they thought they found something, but then it came out a little bit later that no, there was kind of a glitch in the machine to give the wrong number. So. But kind of this computer.
Would have been so mad.
It was like it wasn't calibrated right or something. Yeah, if you're like the scientist, yeah, like something fast in this. Oh no, we just forgot to calibrate the machine. Somebody got fired for that. I'm pretty sure. Somebody got fired for that. So anyway, why is this good for us? Okay, because of this idea of a chain reaction. So what we start putting the pieces together and going, okay. We said that the two important parts of that fission reaction were lots of energy and then 2 or 3 neutrons that come flying out of there. Okay? Why are those 2 or 3 neutrons important? Because how did the whole fission reaction start? With a neutron running into a uranium-235.
How did the neutron start again? We have like.
Say again. Oh!
Remember we talked about.
Okay. How does it all start to begin with? Nick, when we look at the way that certain things, radioactive things, decay, they will give off certain pieces depending on what stage they are and how close they are to being 82 and blah, blah, blah. Okay? Eventually, those things are trying to get down to 82 protons. But sometimes there's a shuffling about the number of protons and neutrons, and instead of just giving off protons, sometimes they'll give off neutrons as well. Okay? So we know that certain things will give off neutrons. So what we do is we get some of that substance, we put it basically like in a box. And then we poke a little hole in the box. And so out of that little hole now comes a stream of neutrons. Because the thing inside the box is giving off neutrons as it decays. And so we can then use those neutrons to get it started. Is that good? Yeah. What else?
So then after like these 2 neutrons come out, they do the same exact thing that just happened.
Yep.
How long does it keep going for?
That depends. Okay? Depends on a couple of things. If there's a lot of uranium-235, right, how long does it keep going? It goes for a long time. And each time it happens, right, more and more energy gets let off, right? If we just keep letting it going, and eventually what would cause that to stop? If you run out of uranium-235s, right? Because we said that's really the atom that has to get split up. If you just let them keep running, you let those neutrons keep running into new uranium-235s and new uranium-235s until all the uranium-235s are gone, right? That's what we call an atomic bomb. Right? Because each time it just keeps giving off more energy and more energy and more energy and more energy. Okay? Now, sometimes we don't want that to happen. Okay? Actually, most times we don't want that to happen. Okay? But there are some times that we want it to happen to a certain degree. Okay? And that's when we get as far as a nuclear reactor is concerned. A nuclear power plant. Alright? So, that's what is that letter? Letter C, right? A nuclear reactor uses a controlled chain reaction. So, this picture that you guys have there is a crude representation of a nuclear power plant. See these purple lines down here at the bottom?
Yeah.
They're labeled as uranium fuel rods. They're made out of uranium-235. And so we start, yeah,
That was on 24.
probably. So, those start the chain reaction. Okay? Then, as the chain reaction is started, it gives off energy. What do we use that energy to do?
Move things.
Nope.
Heat up.
Heat up water. We use it to boil water. Okay? I know that seems kind of, like, seems kind of unspectacular, but that's what we use it for. In a regular power plant, a coal-fired power plant, like the ones today make, we do exactly the same thing, but instead of using fission to heat up water, we use coal to heat up water.
That's the
Okay.
environment.
So, we will continue on with this on Monday. Yes?
How long do those rods
Depends on how big they are and stuff like that, but they do have to change them out every once in a while. Because once the uranium-235s are split, it's no good anymore. So yeah, they do have to change them out every once in a while.